Electronic Music Synthesis by Doug Orlando. Hi! Welcome to Electronic Music Synthesis 1, and welcome to my home studio. And I'm Doug Orlando. We're going to basically be talking about pitch, timbre, and loudness and waveforms as this part of the course continues on electronic music synthesis. In my home studio here, I've got a couple keyboards, the Yamaha DX7 right here, and then also here's the Yamaha DX7. Let's see if we can get it going here for you. There's the Yamaha DX7, and then I've got a Korg keyboard down here, which is a Poly 800. You could see that. We'll probably get a different shot of that in just a little while. Let's see if we can get the Korg on here for you. That's a analog keyboard. So there's our Korg, and then also I've got a remote keyboard, which I'm going to show you how we use this here. This is the remote keyboard. It's called a Yamaha. Let's see, what is the number on it? SHS 10. Now the way this is played, let me get this down a little bit for you. The way this is played is that you can either play it with the original sounds that's inside of the machine, or you can use the remote MIDI. And through MIDI we can play the DX7 or the Korg keyboard from this remote keyboard. Okay? Let me plug it in here for you for a second and give you a couple little demonstration on it. You can see how I'm doing this too in the meantime. Okay, this will turn it on. Now we've got original sounds inside, and there's a little demo here. It's not a bad little keyboard, you know, I mean, really. Now what I'm doing here is I'm going to plug in the MIDI cable to the DX7 here on top. And we'll put just a regular piano sound or something on the DX. Okay, there's the DX7. Yeah, I didn't think that this would play through MIDI. That's like a horn sound or something. There's the ending. Not too bad, huh? Okay, so what we're going to do here now is play the DX7 through MIDI. Okay, now here's the sound of the keyboard. We'll shut that off. Okay, and here's the DX7 now. Just a basic piano sound with nothing. Okay, we got to set the parameters here. We've got MIDI receive channel 1 is what we need on that, because there's 16 MIDI channels, which I think I might have talked to you about before. So here's the piano sound on from the remote keyboard. Now as you can see, I'm using the remote keyboard for this, and we're playing the DX7. See, here's the DX7 keyboard, okay? Now let's see if we can gear up that song through MIDI. Oh, listen to that. See, it's playing the DX7 now and the keyboard. And there's the DX7, and now this remote keyboard is playing that through MIDI, through this cable right here, which is being connected to the DX7 right in there. See? And that's the magic of MIDI, which is absolutely wonderful. Now we can turn up the volume of the keyboard here into the microphone. Now I'll turn off the DX7. Now all we're listening to is the remote keyboard right here. Okay. And then we also have a pitch bender on the end. Okay, and we also have the sustain button, which is right here. And there's portamento. And I can give you an example of that on a different sound here. Let's set the portamento to this mini Moog sound right here. Okay, so that's basically the remote keyboard. So I've got 3 keyboards here that we're going to be taking a look at. Basically, what I do want to show you mainly is pitch, timbre, and loudness, and what those 3 parameters look like on the oscilloscope. And we can also compare it to the Strobe tuner so you can see the pitch of the actual notes. So let's make a couple adjustments here, and in the meantime we'll get a couple things adjusted. Okay, we'll put this one back here. Okay, we're back, and I think we're situated here. Let's just turn this down a little bit. So now I've got the DX7 here adjusted a little bit so you can see it a little better. Okay. By the way, this is a song called The Joy of the Lord from our 5th cassette album, Break Out of the Darkness, and it's all been done by the DX7 and the RX-15 drum machine, which you might be seeing later. Okay, over here on my right and your left, I have the oscilloscope that we're going to be looking at. And then the strobe tuner, which is this item over here, and we're going to be looking at a couple sounds that it can create. I'm going to be reading a little bit from the Learning Music with Synthesizers, and also the Secrets of Analog and Digital Synthesis books. Let me grab those. Okay, the Secrets of Analog and Digital Synthesis book, which is this one right here, I'm sure you all have. And then the Complete Synthesizer, of course, is this book here, which is the first edition of it. The second edition is this one, which is the one that you would also be getting for the class. Okay, and now these are the two books. Now let's take a look here in the Secrets of Analog and Digital Synthesis book. And we want to basically look at pitch, timbre, and loudness in the synthesizer concepts section as one section. Okay, the big three, obviously, right? Which is what we talked about. The big three, okay? And we're going to be looking at wave parameters and what and how that looks on the oscilloscope. Okay, we perceive sounds as having three distinct attributes, right? Pitch, timbre, and loudness. Okay, pitch is obviously the pitch of the note, how it sounds to the ear, high or low, and then we have the timbre, which is the tone color, right? And then, of course, loudness, which is how loud the sound is, or volume. Okay, now if we look at the in the book here, before we look at the actual wave parameters and the wave shapes, let's go through the big three. Okay, now it says, now that we know what sound is, I'm reading on page 11, and how it is transmitted from the source of to our ears, we could take a closer look at the three parameters, pitch, timbre, and loudness. Okay, our perception of loudness is directly related to the wave parameter, amplitude. A sound wave, like all moving waves, is a form of energy. The amplitude of the wave is an indicator of how much power, right, the wave contains at a given moment. And then that power, of course, is represented by intensity, and there's a threshold of sensation, which I'm sure we've talked about, which is the lowest sound that you can hear, or the softest, I should say. Threshold of a sensation, ultra pianissimo, compared to, and then that can be contrasted to the threshold of feeling, which is like mega forte, the loudest airplane sound you could imagine that would, I'm sure, damage your ears at 130 or 150 decibels. Okay, so that's basically the loudness or amplitude. Okay, and that can be described or related to as in decibels. Okay, that is the common measurement of loudness. Now, if we look at pitch, pitch is the wave parameter. Frequency is what that is related to. Okay, and we're going to take a look at all these on the oscilloscope in just a couple minutes. Okay, and then the next thing is timbre, which is the wave shape, the shape of the wave form that it takes, or the tone color. All right. So the first thing we're going to look at, and we are going to basically stick with the Yamaha DX7 initially, because the DX7 is a digital keyboard, and it is so pure that the waveform, well, you'll see in just a minute, is absolutely perfect. There's nothing that you could imagine that makes it distorted at all. Okay, when we look at the analog keyboard, the Korg down here, you will see that the waveform is hardly perfect compared to the digital Yamaha digital algorithm synthesizer, the DX7. Okay, so let me make a couple more adjustments here now, and then we're gonna zero in on the oscilloscope, which is right here. Let me get it a little bit adjusted so we can so you can look at it and look at a regular trace here. Okay. Now, if we can keep those in focus there for you, I think we'll do pretty good and see how it looks. Let me get the microphone out of the way here so that you don't have to look at that if we can possibly do that. Okay. All right, now what we have here is the oscilloscope, which is right here, and we have a strobe tuner right next to it, which is this item. Okay, now we're going to compare the two. Let me bring the strobe tuner forward just a little bit so we can get it in better focus. Okay, I think if they're both about the same there. And we'll see if we can get a pitch that you can check out on. Okay, first of all, I'm going to, let's shut down the strobe tuner for a minute because I want you to zero in on the oscilloscope. Okay, and we're going to look at what a basic pitch looks like. Okay, we can get the DX7 here adjusted. So, since I'm the one playing it and you're not, right? Okay. Now, we're going to look at a basic sine wave. Okay? Just a basic sine wave. Okay, let's get that volume on that. Just make a couple adjustments here. I think we'll be in great shape. Okay. Now there's our waveform. It's a sine wave. It's pure. Okay. Yeah, we'll bring it down there just like that. Okay. Now let's look at the different attributes. As we just discussed, pitch, timbre, and loudness. The first attribute is that we talked about was loudness, or amplitude, correct? Slowly, I will fade in the sound of the DX7 and you will watch the amplitude increase. And there's the sound, correct? Now we'll decrease it and you'll watch the amplitude decrease. Again. So as you can see, the amplitude is the up and down motion, correct? For the oscilloscope. And by the way, the oscilloscope is measured in volts. So what we are looking at is basically 20 millivolts per grade on the grid here. Okay, we have a graphic, I don't know if we can zero in a little bit. I think you could just about see that. I adjust the scale illumination here. You can see the graph on there. Okay, so there is our volume, or loudness, or amplitude. Now the timbre is the waveform itself. It's a sine wave. It's pure. And I'll show you what a not pure waveform or altered waveform is in just a moment. Okay, here we go. But before we get into different waveforms, I want us to stick with the sine wave for a moment and look at frequency or pitch. And I'm going to slowly increase the notes of the C scale, and you'll see there's an octave. See down there on the original octave we have one waveform. An octave higher we have two waveforms. An octave higher than that we have four waveforms. And an octave higher than that we have 8 waveforms. As you can see, we are multiplying by 2, correct? 1, 2, 4, 8. And if we go an octave higher than that, we'll have, what's your guess? How many will we have? 16? If you said 16, you're right. Because we're actually doubling. So this would be 2. Actually, this would be 1 times 1, then 1 times 2. 2 squared is 4. 4 squared, or 4, right? So we're going actually by 2s exponentially. Okay. Okay, let me zoom in a little bit better on the oscilloscope so you can see exactly what's happening. Okay, now we've got the oscilloscope in there for you. I think you're going to be able to see it pretty well now. Let me adjust the scale illumination here, and you could see that the grid goes away. It's like a graph. See, and then there it comes back in. And we're looking at 1 volt per centimeter. Each one of these is a centimeter. Okay, and let's get just a clear straight line there. Okay, and that's 0 is our starting point if we adjust the position. Okay, we'll get that right on the center. And we can adjust the trace position left to right. So we can look at a full trace of the waveform. And of course the focus and intensity. Okay, so we'll set it right about there. Okay, now we're going to flip our channel back on with the switch here. Okay, now we're looking at the DX7 itself, and it's listening to it. Is actually what it's doing. The oscilloscope is listening for the pitch. See? In order to keep it from moving, what we do is we gotta get it triggered. Okay. And there's an octave higher, another octave higher. As you can see, there's 4 sine waves there. 2, 3, 4, 5, 6, 7, 8. And then there we could just barely count if we can get it stabilized. 16, just like I said. Okay. Okay, now let's look at, again, I'm going to show you amplitude or loudness. Okay, and that is on just a basic sine wave, which is incidentally how the DX7 operates FM synthesis, is building sine waves together to make other waveforms, such as the sawtooth, triangle, and square waveforms, and pulse. So what we're going to be looking at now, since you've already seen amplitude and loudness and frequency, okay, now we're going to look at timbre. And timbre is tone color, correct? Which is related to the waveform of the sound. Okay? And now we're going to change the waveform of a sine wave very slowly. First, we're going to make it into a triangle. Okay, that's all it took right there, and we made it into a triangle. There's a sine wave, excuse me, sine wave, and now we made it into a triangle. Okay, we're just slowly, just a little bit of an altering. Can't even hardly hear the difference, can you? Let's try it up here. Oh, there you can hear it just a little. And what are we hearing? We're hearing an overtone, correct? It's kind of like a higher pitch. A higher pitch that's entering the frequency spectrum. It's really high up there, isn't it? Now as we bring it in a little bit more, you'll see it turn into a, first it'll start as a sine wave, and then we'll go to a triangle waveform, and then we're going to slowly move it into a sawtooth waveform. Starting with sine wave. There's our triangle. And now we're moving it into a sawtooth. Okay, which is even more overtones. There's this, we'll do it up another octave, a little higher frequency. There's our sine wave. Triangle, sawtooth. Now as we increase harmonics or overtones, the waveform gets more and more complicated as we go. Okay, let's bring it down a little bit down here, and then you can tell a little bit better. As we increase it, we bring in more harmonics, and it gets more and more complicated. Let's go up an octave, and then you can hear it a little bit better. There's our triangle. There's our sawtooth. Now we bring in the more and more harmonics. Back to our original pure sine wave. Let's bring it up another octave. The waveform gets so complicated that it's impossible to even tell what it is. And that's how we make such peculiar waveforms with the DX7. The other element here I was going to show you that I just realized on pitch, we have a pitch bender, which will give you a good showing of how pitch changes and what it looks like. Okay, here we go. Let's see if we can get it triggered here, and we'll sweep the pitch of the note. Now you can see there that the pitch is changing. Let's lower the speed a little bit. If we can try to keep it triggered. There you go, see? There you go, now you can see that it's moving back and forth, kind of like an accordion, wouldn't you say? If we could just keep it triggered there, we don't want it to jump all over the screen. There you go. See, it's looking like an accordion. And that's kind of what happens for pitch, when pitch is changing. Okay, there's just a little bit. See, it's just moving back and forth, just a little bit. And that's how the frequency is changing, see? So that's what pitch and frequency is corresponding to. That's another little demonstration on that. Okay. Now let's look at a little bit as we sweep as I was showing you here, let's go back to the sweeping the frequency spectrum. Okay, we started with a sine wave. Now we're going to look at and make a square waveform. Okay, there you go. See how a square wave looks. There's a sine wave. And we'll slowly make it into a square wave. See how the top rounds out? Well, actually it's rounded there. We're going to flatten it out. That's what we're going to do, right? Here we go. Now, technically, we end up with these three little kinks, which is something that seems to be inerrant on the DX7. See those kinks on the top, and then on the bottom. And in order to flatten those out, I kind of cheat a little, and I add what is called feedback. Okay, and here's feedback. Slowly I'll increase our feedback. Okay, except, let's see, we've got one alteration we need to make, and let's see how we're going to get it. Time out, there we go. Okay, and feedback. Okay. The DX7, as we've said, isn't really as easy as most other synthesizers. There we go. Oh, wow, look at that. See how we rounded out those edges? See, technically we've got those three kinks in there, and we can round them out and make it into a pure square wave. There we go. There's our sine wave, and there's our square wave. It has kind of a hollow sound. It's kind of like a clarinet. And then we can change our pitch. And there's an octave higher. And what the square wave looks like. as you notice, if we play chords, we get all kinds of overtones moving all over the screen. You can kind of lower the amplitude there, and then you kind of can see what's going on. Oop, we lost the trigger. That's because it's a little bit too soft. There we go. Now I'm going to show you one other thing, and then we're going to be able to have you try it on the DX7 yourself in a little bit. And that is, I want to bring some chorusing into a sound. We're going to detune slightly one of the oscillators or operators, as we call them on DX7, and then you'll see what happens. Okay, and slowly we're going to detune it, and you can see it's changing a little bit. And what happens is we kind of pulsate. If you listen to it, you can hear that it has a little pulse to it, can't you? We'll slow it down to nothing. We'll slowly increase it, just a little. And we can make it faster and faster. And you can hear that pulsating overtone. What we've done is we've detuned it slightly. And that's typically what a piano does. Obviously, the notes aren't perfectly in tune on an acoustic piano, hardly. The whole object of the acoustic piano is to have somewhat of a oscillation or undulating sound overtones, and that's what gives the warmth. And that's what we do on a synthesizer when we synthesize certain instruments, is we need to build in the inherent mistakes, if you will, of the instrument. There's a slow detuning, and then we make it faster and faster. So let's just look at a couple sounds just to show you what they look like. Here's a basic piano sound. Let's see if we can get it triggered for you. See, if we start playing chords, it's going all over the place. So we'll just look at a couple notes. Okay, there's our basic piano sound. Let's look at a couple other ones. This is kind of a good one. That's kind of like a horn. Okay, the way we have this one set up. Okay, I've got that one pretty. There we go. I've got that one set to start, and then slowly change as we go, see? Okay, it's kind of like a clavinet. And then we bring in the overtones slowly with the envelope, which we will be talking about a lot more as we get moving in the course. You may already have heard envelope. See, it starts out kind of a basic sawtooth, and then it gets a little brighter. Here's a bass sound. It's pretty much a sine wave, as you can see, and then we may put a little bit more frequencies in there. And then as it slowly fades out, it pretty much fades out into a sine wave, doesn't it? And then we go right into a sine wave. Okay, let's look at, here's one that really is moving all over the place. Okay, let's look at a couple other sounds real quick. There's a piano sound. And then it has kind of some extra frequencies coming in. Okay. As you can see, if you really want a nice sound that does something, you want to have some sort of change to the sound as you sustain a note. All I'm doing is have my thumb on middle C right now. And with my thumb on middle C, we slowly start with kind of a plain square or sine wave, and then we bring in more and more harmonics as the sound is held down until finally we've got all kinds of things going on. It's kind of a nice lead sound. And then of course, there's some other kind of horn sounds. Basically for brass instruments, we use a sawtooth as a starting point. As we synthesize orchestras, in order to synthesize a full orchestra, we definitely need a lot of chorusing and movement in the sound. Now, if the sound was not moving at all, let's see if we can stop it for you just for a second. You'll see that instead of several violins or fiddles, the sound will sound just like one violin because we've stopped the detuning effect. It's still moving. Now we're the last one. Okay, it looks like that's going to be kind of a tough one to stop from moving unless we do that to it, because this is an FM synthesis sound. There we go. We pretty much stopped it there. As you can see, it slowly is going to become a sine wave as you watch it. Let's watch it for a minute and see what waveform we might end up with. It may not go all the way down to a sine wave. Looks like we're going to stop about there, which is kind of like a half triangle sawtooth. So that's a basic violin sound. Then we have our guitars. Let's try this one. As you can see, that sound begins and then slowly just kind of fades out. Almost kind of looks like a couple of guitar strings vibrating there, doesn't it? So as you could see, the actual sound, the actual waveform, there's a marimba. That's pretty much like a sine wave, isn't it? As you can see, they're not pure waveforms as you're learning sine wave, sawtooth, triangle, pulse waveforms. If you really want to synthesize a sound, it needs to be a little bit more than just a basic waveform. But these waveforms give you a starting point. As you can see, that marimba sound is very close to a sine wave. It does have some jagged edges, though, as you could see. That edge is a little bit jagged. Okay. Now basically, what I also want to show you is just to contrast this with the strobe tuner. So let's just take a quick look at the strobe tuner in conjunction with the oscilloscope. We'll make a couple adjustments here. Before I show you the strobe tuner, I almost forgot that I wanted to show you the digital multimeter. This digital multimeter is a Fluke meter, and the way it's set up is we look at the, I think you can almost see the, right, okay. We're looking at DC voltage. On your basic analog synthesizer is 1 volt per octave. So a middle C, that note right there would be 1 volt. And then an octave higher, that would be 2 volts. And then an octave higher than that would be 3 volts. An octave higher would be 4 volts. And then what would this be? 5 volts, right? Now, technically, the DX7 is not an analog synthesizer, obviously, so we're not going to be looking at control voltage. But on many synthesizers, control voltage is very important, and that's why we have the digital multimeter where we can look at AC volts, DC volts, ohms, megohms, and this is our range switch over here. So if we set it to DC volts, we've got our probes, and these are our probes that we would connect positive and negative leads to on our control voltages. Okay, now we're going to get back into the strobe tuner as I was showing you, as I promised you. Okay, we're back. This is the strobe tuner. It's a Peterson strobe tuner. Basically is about all I could say. This knob here, if we look at, is the note right here. We have it set to an E. I think you could just about see that. That's a note E. If we try not to move there, we'll get that in focus. Okay, we have it set to the E note. Let's see if we can get it in focus there so you can see it stop. That's going to be kind of tough. Okay, there, you can just about see it. And that's showing us that the note is in tune. Let's go back to our sine wave right here. And then you'll be able to see, let's see, where are we? Okay. Our basic sine wave is a voice edit recall. We've got so many things here to do. It's on the DX7. It's hardly nothing is ever quick, it seems. Okay, there's our E. Let's look at let's switch the note number, or note name I mean, to, let's see. I think you could see down here what note we're going to. Let's go to C. We'll just put it on middle C. There we go. Okay. This adjustment here is called vernier, which is sense, sharp, and flat. And I'll show you as I turn that knob what happens. We're going to zero in on the indicator here. I'm going to try to zoom in on that a little bit better because it's kind of hard to see because of the lighting. Okay, now I think we'll be able to see this. You'll be able to see this a little better. Okay, there's our C. Okay. And okay. We could just about see that. All right. Let me see if we can adjust the lighting in there just a little. It may look a little bit better if I can just switch it a little darker here. Okay, let's try that. Okay, now you can see that the strobe tuner stops. Okay, there's our lower octave. Look at the one that stopped. There's the higher octave. You can see that one that stopped. Let's see if we can get the higher one in there. Oh, that's a little hard to see. But there's our lowest octaves. Let's put that switch back. Okay, I think you can just about see then. That's a low C. There's our next C. There's our next C. Another higher C. And that's the extreme high one. And that's how we use a strobe tuner. Now let's compare the strobe tuner. Well, first, you can see how perfect that is stopped. Let's make it move a little bit. Ah, it's flat, isn't it? Is it flat or is it sharp? Why is it flat? Because what? There's our flat sine, right? And here's our sharp sine. Right in the middle is perfectly in tune. Okay, and A440 is 440 hertz, and that's what that says right there, A3. So as we slowly make the pitch go flat, it starts moving, correct? And the same with sharp. Let's move it just a little bit with the detuner. There you go. See, that's just a little bit. And that's how we tune instruments, correct? When we say, oh, you're a little bit sharp, we'll slowly bring it in tune. And the same with bass instruments. Or a high instrument. If you want to play a high flute, there's sharp. Or flat. Okay. Now I'll pull it back a little bit and we'll look at what the oscilloscope and the strobe tuner. Okay, we got them both in there now. Oh, you can even see that the strobe tuner is stopped, right? Now let's move it up another octave. See, and you could see the strobe tuner changed, and so did the oscilloscope. And now let's move it up another octave. Well, we can't really see the strobe tuner too well on that, but we can on the oscilloscope. There's the strobe tuner octave, and now one more octave brings it down, and then down again. As you can see, the graduations start here, and then they move up for another octave, up for another octave, up this way for another octave. The numbers here range 0 through 7. So we actually have 8 octaves in the hearing range, technically, that the strobe tuner will show all the way up. Again, one more last time. There's a real low octave. This one's called C0, C1, C2, C3, C4, and C5. And again, as we bring our harmonics in, it's almost a little bit easier to get a look at the sound when we bring those harmonics in. Let's do that again. can see how the strobe tuner changed also. It's almost a little bit confusing on the strobe tuner because it keeps moving. So you can see it's looking at a higher octave on that one now. That's why it's a little easier just to get you can get a perfect sine wave or close to it. It's a little bit easier to check. So there's the difference there between the strobe tuner and our oscilloscope. It looks like that's just about all for now. Thanks a lot for coming to my home studio and taking a look at a couple different things on the oscilloscope, the strobe tuner, and the digital multimeter. There you go, now you can see it. The remote keyboard and the DX7. Before we go, I want to just show you a real quick difference between the DX7 and the Korg, and you'll see how the analog synthesizer differs. We'll take a quick look at that. Okay, I've got the Korg plugged in. I'm just going to show you in one quick second here what the Korg's going to look like. Let's turn up the volume to the Korg just for a second here. Okay. There's the Korg. Okay. Maybe you can hear it pretty good. Let's turn it down to the oscilloscope a little bit so we can just get a particular waveform. Okay, we'll make a slight camera adjustment here. Just so you can see the graduations of this, this will be kind of interesting to you. Okay, here we go. All right. Now, there's our Korg. Now we're going to have to make a couple adjustments here. Crank it up. Turn it down over here. Okay, there you go. And if we turn off our chorus and all this good stuff, then we could just look at a basic pitch. Okay. What kind of waveform you think that is? Doesn't that kind of look like a... Well, take a look in your book. Take a look at your book on the Secrets of Analog Digital Synthesis on page 6, Wave Parameters. On the parameters there, we've got pulse, sawtooth, sine, and triangle. And which one does it look like? Kind of looks like a sawtooth, doesn't it? Yeah, if you said sawtooth, you're right. Let's see if we can trigger it. There we go. So that is our basic sawtooth on a Korg. And if we chorus it, you can see that the pitch is changing all over the place. Which is somewhat the same as detuning. Let's see if we could put it in detune mode. There you go. Now we detuned it. So that's a sawtooth. Let's see if we can take a look at a square wave and see what that looks like on this analog synthesizer. Okay, now we just switched it to square. It really doesn't look too bad, does it? Except, let's see if we can get some of those higher notes out of there. That's a little bit better. Yeah, that isn't too bad, really. That isn't too bad. And as you can see, as we increase the frequency, we increase our number of waveforms right on the screen. And frequency again, which is going to change the placement. And then our amplitude, of course. Okay, well again, I'd like to thank you for just being a part of this electronic music synthesis demonstration, looking at the oscilloscope, the Korg keyboard, and the DX7, strobe tuner, and the digital multimeter, and a little bit of MIDI. I'm Doug Orlando. Thanks for being here.